Now I'm going to talk about something very scary, but don't be scared. It's called Jupiter's energy crisis. So a lot of people didn't even know that Jupiter had an energy crisis, and most people still don't know. So you'll be one of the first. In fact, all the giant planets have what we call an energy crisis. It's only a crisis in the sense that we don't understand where this extra energy comes from. So specifically, the temperatures in the upper atmospheres of the giant planets have all been observed to be much warmer than we expect them to be. So at Jupiter, for instance, it's 5 times further from the sun than the Earth is, which means it should receive 25 times less solar radiation or solar heating from the sun, and yet its upper atmosphere is around the same temperature as the Earth's upper atmosphere. So obviously there's an additional source of energy at Jupiter that helps explain why the upper atmosphere is so warm. The crisis is we don't know what that extra source of energy is yet. I show in the table here what the observed values are and the modeled or theoretical values are for each of the giant planet upper atmospheres, Jupiter, Saturn, Uranus, Neptune. And you can see that there's a discrepancy on the order of 240 Kelvin up to almost 800 Kelvin at each of the giant planets. This is, you shouldn't take the numbers too precisely here because depending on which part of the upper atmosphere you measure, in terms of latitude and longitude, you might get a different temperature. Temperature would also be variable with time, and so on and so on, okay? But just order of magnitude, we're talking about temperatures where the observations are at least hundreds of Kelvin larger than what we think the temperature should be. So, in other words, that means there's an unknown source of heating for all the giant planets. It might be the same unknown source at all the giant planets. It might be different combinations of sources at different planets. It might be anything in between. Anytime we don't know the cause of something, as scientists, we're interested in figuring that out. And often, when you do figure that out, that leads to a lot of other interesting implications. So, we call it a crisis in understanding, but we use the motivation often of it being something that we don't understand, meaning that it's something worthy of trying to understand and therefore researching. Okay? So people have put forward various theories about what might be causing the excess heating in the upper atmospheres of the giant planets. For example, the Earth has auroral emissions. So you've probably heard of the aurora borealis or the aurora australis. Okay? Auroral emissions are an atmospheric signature of a process that links the space environment and Earth. And ultimately, in the case of the Earth, it links the sun to the Earth. So basically, what happens in an aurora is some combination of space processes introduce energetic particles into the environment around the Earth. Those processes might be, for example, the sun undergoing an extreme explosion event on its surface. So you've probably heard of solar flares. There's also other solar storms that can happen called CMEs, or coronal mass ejections. So the corona is the outermost envelope of the sun's atmosphere. It's very hot, very turbulent, very energetic. The sun is constantly, essentially, spewing off these charged particles, and they just radiate, they flow away from the sun in what's called the solar wind. So there's essentially a wind of energetic charged particles always coming radial outward from the sun, containing also magnetic field. This wind can impact some object in space, such as the Earth, and it can cause interactions with that impediment to its flow. So in the case of the Earth, we've talked about the Earth having a dipole magnetic field. The magnetic field of the Earth acts as a barrier to the charged particles and magnetic fields of the sun, and so it creates a shell or a sort of teardrop-shaped structure wherein the Earth's magnetic field is dominant within, and the solar wind's magnetic field and plasma environment is dominant without. And that structure is called the magnetosphere. So any planet that has an intrinsic magnetic field will have a magnetosphere. Okay. What happens when there's an extreme event in the solar wind, such as a coronal mass ejection? So there might be a sort of steady solar wind leading to a sort of steady structure in the Earth's magnetosphere. But then a CME happens, and suddenly there's a density enhancement in the solar wind. All right? And that density enhancement slams into the magnetosphere of the Earth, and it reconfigures everything, and things change around, and ultimately introduces, during this reconfiguration, some energetic particles are introduced into the Earth's magnetosphere, and charged particles tend to have to follow magnetic field lines because they feel electromagnetic forces. Since the Earth's magnetic field is essentially dipolar, that means there's magnetic poles, a northern and a southern magnetic pole, where if you were to draw equipotentials or magnetic field lines, they would come out of one pole and go into the other in what's called a dipolar shape. The poles of the Earth's intrinsic magnetic field are relatively close to Earth's geographic poles. Okay? So there's a magnetic pole and a geographic pole. Magnetic pole is relatively close to the geographic pole. Magnetic pole is where these field lines are coming out from, in a sense. And so if you're a particle flowing along field lines, you are sort of directed to go towards these polar regions. Okay? So all of that is a long-winded explanation of essentially what is charged particles coming from the space environment, following magnetic field lines, impacting the Earth's atmosphere. That impact, as they impact the atmosphere, they sort of cascade around like a billiard ball, lots of different collisions, and they give some energy here and lose some energy there. And ultimately, some of that energy is then re-emitted in the form of radiation that we can observe with our eyes. That's the aurora australis or aurora borealis, or even in different wavelengths as well, like UV, infrared. So that process happens at all the planets with intrinsic magnetic fields. So Jupiter has very, very powerful aurora, in fact, the most powerful in the solar system. And that process, that of particles colliding with the atmosphere, losing their energy to the atmosphere, represents also a process of heating. So it's not directly from the particles themselves, but from the currents that this whole interaction drives within the system. These currents can deposit lots of energy in the upper atmosphere, because the upper atmosphere is where auroral emissions occur. So that's the main hypothesis for where this extra energy comes from. That is auroral energy deposition driving currents in the upper atmosphere. And so the magnetic polar regions of Jupiter or the other giant planets should therefore be really hot. And in fact, models agree with this. They easily predict very warm polar regions. And then maybe the rest of that energy is just sort of redistributed globally somehow. Okay, maybe. We'll see why we think that might not be the case in a minute. But before we get there, another commonly proposed source of extra energy of the giant planet is due to the lower atmosphere. Lower atmosphere has all sorts of wave activity occurring. For example, it could be gravity waves, or it could be acoustic waves. Gravity waves, we should emphasize, are a very different process than what you may have heard of referred to as gravitational waves. So these recent discoveries of, for example, black hole mergers, two black holes orbiting each other rapidly and then merging, generate a wave in the gravitational field. Those are gravitational waves. Those are not what we're talking about here. Gravity waves are more or less fluctuations in the atmosphere itself, where the restoring force that sort of drives that wave and puts energy into the wave is gravity. Okay? Acoustic waves are what we're more familiar with, but maybe not thinking about them in a wave form. That's waves where the atmosphere, the gas is moved forward and backward, just like I'm talking with you now. Those are acoustic waves. But lots of processes generate acoustic waves. All these different waves might ultimately propagate into the upper atmosphere. And just as you might know from waves in the ocean, where they build as they get nearer and nearer to the beach until they're eventually too tall and then they break, waves that propagate from the lower atmosphere to the upper atmosphere undergo a similar sort of breaking. And when they break, they deposit some energy. So this might also be happening at the giant planets, where the lower atmosphere is transporting energy upward in the form of waves. Okay, so let's evaluate some of those different situations. First, the possibility that auroral energy deposition processes heat the magnetic polar regions, and then that energy is somehow redistributed globally by winds or whatever processes. Okay? Now, that does happen at Earth. We see auroral heating, and some of that heating is transported towards the equator. Those winds, those polar to equator winds, are called meridional winds. The east-west winds are called zonal winds. So what we see at Saturn, however, at least according to global 3D model calculations, is that we can't transport that polar energy equatorward, because what happens is that all the giant planets are rotating very rapidly. And what that means is that the Coriolis force on these planets is very strong. So Coriolis force is sometimes called a phantom force, but essentially what it means is that, let's imagine you start out going meridionally, which is so moving from the pole towards the equator. The Coriolis force will turn what is just a north-south meridional motion into more of an east-west motion. Okay, so it deflects winds that might be coming from the poles, winds that originally start out as meridional or equatorward winds, they get deflected to be zonal winds by the strong Coriolis forces on the giant planets. At Saturn, people try to model the effect of auroral energy deposition in order to see if that would resolve the Saturn energy crisis. And what they found is that it actually made it worse. So it's kind of complicated, and we have a few figures here that I'll walk you through carefully. But first, in general, remember that the shape of the giant planets, so their non-spheroid, called oblate spheroid shape, is due to their rapid rotation. And so their radii is largest at the equator because the centrifugal forces there are largest. When you get towards the pole, in other words, the rotational axis, the centrifugal forces are small, and so they have no role anymore on determining the shape of the planet. Okay. So that shape, because it's determined by the rotation, it means that the particles that make up your atmosphere need to keep rotating at that speed in order to maintain the shape. So what happens at Saturn in these models, these are 3D global circulation models of the upper atmosphere. What happens is you generate ionization near the aurora due to this initial energy deposition. So energetic particles come down and ionize the atmosphere. So they create an abundance of ions. The ions, remember, are tied to the magnetic field, meaning that if the magnetic field rotates, they have to go with the magnetic field. The neutrals, on the other hand, don't care so much about the magnetic field. And so they just do whatever they want. And what they want to do is to continue rotating based on what they have been doing, and that's Saturn's rotation. So that means that there's going to be a relative offset between the rotation velocity of the ions and the rotation velocity of the neutrals. And that offset means the ions and the neutrals are going to collide. And so those collisions lead to an eventual slowdown of the neutrals. So if you're a neutral particle somewhere in the upper atmosphere, and you're rotating at a certain rate, and that helps describe the oblateness of Saturn, and then you start colliding with ions, and you lose velocity, that means you have to fall inward. And so that inward motion then causes extra motions to follow for the rest of the atmosphere. So, right, for example, if you collapse inward, then other particles of gas are going to come to fill that remainder. And the net effect is that these ion collisions slow the neutrals collapse, and they have to draw gas from nearby locations to replace that gas that was slowed. And that ends up drawing energy from nearby locations, whether it be higher latitude or lower latitude. And so this ion drag on the neutrals, which then draws the energy from high and low latitudes nearby, ends up cooling the low latitude thermosphere at Saturn. Okay? So now to back it up, when you start with an auroral energy deposition at Saturn, you generate ions. Those ions and the currents that follow generate lots of heating locally. However, ions there and elsewhere in the ionosphere slow the rotation of the neutrals, causing an inward collapse of the neutrals and setting up a circulation cell that ultimately cools the lower latitude thermosphere at Saturn. So in other words, auroral energy deposition makes the low latitude thermosphere at Saturn lower than high. So it doesn't help the problem, it makes it even worse.